So, come back to second half of this lecture. I will now restrict myself to the linear maps from the same vector space to same vector space. So, those are called endomorphisms, or those are called linear operators on a vector space V. We will assume V is finite dimensional. V is a basis numbered by finite index set I, and we consider a linear operator F from V to V, K linear operator. And then we have, to this linear operator we have associated a matrix M V V F. This is a matrix of F, Aij, Ij, both are elements in I, the same basis, no. So, for each j in I, f of Vj is the jth column, that is Aij Vi. So, we have given, so what is the, suppose I take F equal to identity map IDV, then what is the matrix MVV of the identity map. This is, I just have to know where Vj goes under identity. Vj goes under identity to Vj only. So, that means this is a matrix where it is a delta Ij matrix. Here delta Ij is a Kronecker delta. This matrix also, when I is a standard finite set 1 to n, this is the matrix 1 1 1 on the diagonal, it is n cross n matrix, and everywhere else it is 0. Such a matrix is called identity matrix. N cross n identity matrix, or I cross I identity matrix. The name again comes from because it is identity map. And this is the standard notation for this I will use is EI, that is for the identity matrix, or En when I is the standard set 1 to n. And also it is clear now, just now the rules what we saw, it is clear that if I have EI times arbitrary Aij matrix A, then it is A, where A is I cross J matrix. Similarly, any matrix B times identity matrix I, EI is same as B. This B now has to be J cross I matrix. So, these are simple. Now, I want to state a theorem to remember. So, this is a theorem. So, K field I finite set maybe you can call n to be the cardinality I, and then we have defined a map from endomorphisms of the vector space V. V is the vector space, K vector space with basis V, Vi numbered by the finite set I, and then we have a map from endomorphisms to the matrix, square matrices, I cross I matrices, the field containing the field K, namely F goes to identity matrix, the matrix of F with respect to the basis F. This is Aij. And what I want to say that this map is isomorphism, this map is bijective, isomorphism of vector spaces, that is it's a k-linear map and bijective, and moreover I want to say that it respects addition, multiplication. So it's also k-algebra homomorphism, k-algebra isomorphism. Not only it is isomorphism of vector spaces, but it is isomorphism of rings. And remember, isomorphism of rings means it respects addition, it respects multiplication in the ring, identity should go to identity, and that we have checked just now. If I identity map, it corresponds to the identity matrix EI. So that is very important. So it's a k-algebra isomorphism. In particular, their dimensions are same. So in particular dimension of the endomorphism vector space equal to dimension of the matrix algebra. That is the reason this is called a matrix algebra. Over K, I cross I matrix algebra if you want. And this dimension we know, this dimension is same thing as dimension V times dimension V. In general, we have checked earlier that dimension of home VW is dimension V times dimension W. So this is dimension V whole square, which is cardinality I whole square. So this is also dimension of the matrix algebra. And what is the basis? Then the basis of this should have so many elements. So if cardinality I is n, this should have n square basis elements. So let us write down a basis of this matrix algebra. Now we think in terms of matrices. So why n square? You take any two indices between 1 and n, not necessary, or you can simply say I comma j is in I. And then to this pair I want to define a matrix units Eij. This is the matrix where ijth entry is 1, this is ith row, this is jth column, and this entry here is 1, 1, and everywhere else it is 0. This entry here is 1. This is called a matrix ijth matrix unit, and it is obvious that every I cross I matrix, these matrix units are defined for any not necessarily square matrices, and this it's obvious that any matrix is a linear combination of this in a unique way because the entries. So this is a basis. So in general, let us write down. In general, Eij, they are I cross j matrices, I in I, j in j, only ijth entry is 1 and everywhere else it is 0. It is like a standard basis. If you think this as k power I cross j, this is a standard basis of k power I cross j, standard basis, k basis of k power I cross j. And which map do they correspond to? You should always think both ways. So this should correspond to a linear map F from, I want to give some other name, Eij, let me give. Eij, small Eij. should be a map from, or not small eij, small epsilon eij. This should be a map from k power j to k power I. Ij finite sets. If not, you put a round bracket here. Here standard jth basis Ej, that should go where? That should go to the 1, and all other guys should go to 0, and Ek goes to 0 for k not equal to j. So, if we write down a matrix of this with respect to the standard basis, that is precisely these matrix units, because this will be the jth column. Jth column here is precisely will have 1 in the ith place. No, this is not quite correct what I said. Not 1, but E I, where I, this EI is the standard basis here and this EJ is the standard basis here. See, that is sometimes a problem when you have the similar vector spaces standard basis notation. So, this one and the remaining guys goes to 0 vector. So, therefore, jth column in this matrix of again I have written this k wrongly, this should be small ij. This is the vector, the jth column is the standard vector EI. That means at the ith position here 1, that means ith row has 1, and this is a jth. So, this is this. These are the matrix units. Okay. So, and we know the dimension, we know this. So, now if you want to make a calculation, for example, in the, okay, so that's all. Then I want to go on to now the invertibility. Now the invertibility. So, now we have seen that if I take the I cross I matrices, square matrices, MIK, this is a K algebra. You know how to add, you know how to multiply, you know how to scalar multiply. This is a K algebra, and this K algebra is isomorphic as algebra to NKV, where V is finite dimensional vector space with basis is numbered by I. Or also you can think more concretely, this is isomorphic to N K power I, this vector space K power I. This is the standard model for a vector space which has a basis numbered by the set I. Okay. This is a K algebra. So, therefore, and it is not commutative. If cardinality I is at least 2. This one can see it very easily from you can you can write down 2 by 2 matrices, for example, whose they do not commute the matrix multiplication. So it is not commutative, that is not so good, but on the other hand we have to deal with it to study the linear operators on a finite dimensional vector space. So, therefore, it makes sense to talk about the invertible elements. So, invertible elements in Mi K, what are they? They are matrices who should have inverse. That means, so you remember our notation in general Mi K, and then we put a cross here. This is the set of all matrices A such that there exists a matrix B in MIK again such that both the products AB make sense, that should be identity matrix, and also BA, both should be identity matrix. And because it is a non-commutative algebra, both these equations are necessary, this and this, because we do not know this is commutative or not. So, both the equations are important, we cannot say only one equation. In commutative case, one equation is enough, because the other equation is a consequence from the commutativity. So, this is, and remember this I want to denote by GLIK. This is the definition of GLIK, and this is a group under multiplication. Of matrices. That is true in general. We have seen if you have a ring R, then R cross, the set of all invertible elements in R with respect to multiplication, form a group under multiplication of the ring, and that group is called a unit group of the ring A. We could have done this, and remember a notation for the corresponding end Vk. The linear operators on V which are invertible, they are called automorphisms. So, they are aut Kv. This is the set of all automorphism of V, and they will correspond to each other. Okay, that is one thing. Another thing I want to make a comment for the future. See, a definition of GLIK is all those matrices which are invertible. That means there is a matrix B, so that AB equal to identity matrix which is also BA. Now, it is not very easy to check for a matrix to be invertible from this definition, because we have to find a matrix B and we have to multiply both sides and then check both the sides are identity. This is lot of checking is involved. If one want to check quickly, then after one or two lectures I am going to introduce a concept of determinant, and that determinant will easily check how do you check that the matrix belong to the GLI or not, and that will be at the cost of the determinant, computation of the determinant. So, this I will do it when it is necessary. Okay, so, but before that I want to little bit put hands on the calculation with the inverses. So, if A is in GLI, invertible matrix, that means there is a matrix B with AB equal to identity and also BA is identity. And you see this B is uniquely determined, unique. The same proof as how you prove in a ring, if a inverse exists, it should be unique. That therefore, this B is denoted by A inverse, A power minus 1. And then these two equations becomes A times A inverse equal to identity matrix, also equal to A inverse times A. And again standard formulas like inverse, and then take the inverse of that, you get the original matrix. This is nothing to do with matrices, this is in general true. In any ring, whenever inverse exists, the inverse of the inverse also exists, and you get back the original element. Similarly, inverse of identity matrix is identity matrix itself. These rules have nothing to do with matrices. This is in general true in any ring R. Similarly, how do you compute if you know both A and B are invertible, two matrices invertible, then their product is also invertible. This is again no big deal, it is a group under multiplication. And what is the inverse then? And AB inverse is B inverse times A inverse in the other way product. This is because it is not commutative. In a commutative ring, this will not be the case. Okay, now therefore, it becomes a question is, given a linear operator f V to V on a finite dimensional vector space, and if we have given a basis V numbered by finite set Vi I in I basis. Suppose we know this f is automorphism, then we definitely know the matrix of f with respect to this basis, which is a matrix in Mi k, this is invertible. And how does one check this? So, because f is an automorphism, f compose, there is a map in the other direction G V to V, this f, so that f compose G, which is identity map on V. Similarly, G compose f is a matrix, identity matrix on V. That is the definition, because this is an automorphism. It has the inverse map, and that inverse map is nothing but G. Now, when you apply the matrix, apply this map MVV, that means MVV of FOG equal to MVV of identity, and that is also MVV of GOF, but MVV of identity is identity matrix, and this we know it is product of these matrices. On the other hand, it is also this MVV G times MVV F. This, therefore, this matrix is invertible, and this is the inverse of that. So, therefore, what we have proved is, let me write on the next page, it is an important formula. What we have proved is, if f is an automorphism, then M V V f inverse is equal to M V V f inverse of that. So, inverse I can take out. So, this is very important. Okay. Now, I just want to do little bit about matrices. So, just now I said that to check a matrix is invertible, we have to find a matrix B, so that AB is identity matrix and BA is also identity matrix. Still I want to do it little bit economical. So, that is where I state this theorem. So, theorem, that is where the linear algebra is useful. So, I finite set and A is a matrix in MIK. Okay, then the following are equivalent. One, A is invertible, A belongs to GLIK, that is A is invertible. to there exists a matrix B in GLI, not GLI. There exists a matrix MIK such that B times A is identity matrix. That means also this is also said in general that A has a left inverse. In general, left inverse of an element in a ring A is an element. When you multiply that element by left, it becomes identity. The other side we do not know. So, such an element is called a left inverse. 3. A has a right inverse. In the algebra MIK. That is, there is a matrix C such that A times C is the identity matrix. So, these three conditions are equivalent. So, that means our checking is reduced to only one equation, but this is special only for this algebra, and that is because, so proof. So, let me complete still more statement. Moreover, if either, so if 2 or 3, anyway we are going to prove they are equivalent, and 2 and 3 are numbered by not by this but Roman. 2 or 3 is satisfied, then B has to be A inverse or C has to be A inverse. So, what does this mean is, if 2 is satisfied, that B is the inverse of A, if 3 is satisfied, C is the inverse of A. And proof is very simple. Instead of a matrix A, I am going to think a linear map Fa. This is from k power I to k power I. And this matrix A is so for example, invertible, that will mean this is an automorphism. So, and left invertibility means B times A is identity matrix, should mean there is a map. The map is, of course, the map is FB. FB if I compose these maps, FB compose FA, this is nothing but f of B compose A, B times A, which is f of identity matrix, which is the identity map of k power I. So, that means this map, that is the map FA, is injective, because when somebody goes to 0, then I compose with this and it still go to 0. No, but this is identity, so that element itself is 0. So, this condition, the composite map is identity, is equivalent to say that this map is injective. But now you are in a finite dimensional vector space, an injective linear map is bijective. So, since I is finite, Fa is bijective. That means Fa belongs to the ORT, but that will mean the matrix which is A will belong to GLI. That means A is invertible. So, this proves 2 implies 1. Similarly, 3 implies 1, because instead of injectivity the other composite identity will mean that it is surjective map, and finite dimensional vector spaces surjective injective is equivalent to bijective. So, similarly, so this proves 2 implies 1. Similarly, similarly 3 implies 1, and of course 1 implies 2 and 1 implies 3, they are trivial. Okay. I think we will stop, continue next time. Thank you.